Alright, so comparing functions. The first one that we want to talk about is linear functions. Linear functions are the functions that we look at that are in a straight line, okay? Just like you would think about in a regular equation, we think about the equation being y equals mx plus b. Okay, y equals mx plus b. Does anybody remember what that's called, that y equals mx plus b? We talked about it the other day. Slope-intercept form. Okay, that's just your general equation. A lot of times you'll see this equation, this slope, INT form. Okay, that y equals mx plus b. Okay, remind me, m stands for slope, and b stands for y-intercept. Okay. Now, the shape of this is linear. Okay, linear. Think about it. We got a linear function. The shape is going to be linear. What that means is a straight line. Okay, a straight line. Okay, the rate of change, how it moves, because it moves in a straight line, that rate of change is going to be constant. So how we move from one point to the next will always be the same thing for a linear function. Okay, so that'll be constant. Okay. For your x-intercepts, you have a couple of different options. You could either have 0 x-intercepts, you could have 1 x-intercept, or you could have infinite x-intercepts. Okay. We know x-intercepts are the same things as solutions. Okay. So it's saying I can either have no solution, 1 solution, or infinite solutions, okay? And we just saw that, right? That last problem that we just worked was a linear function, and we said that it was x is equal to 14, right? That one that we just did the calculator strategy on, we said x is equal to 14. What that x is equal to 14 is our x-intercept, our solution, okay? Let's see, then we got number of y-intercepts. Okay, you can have one y-intercept. Okay, one y-intercept. Okay. Let's see, number of vertices. Our number of vertices here, there is no vertice because it's a straight line. Okay, that was basically saying, do we have a minimum or maximum? Okay, it's in a straight line, so there's no minimum or maximum. Okay, so number of vertices would be 0. Okay. The domain, how far left, how far right, so we can write left to right. Okay, that's going to be all real numbers. Okay, and then the range is from, we can write low to high. Talking about our y values. Okay, that range could be either all real numbers. We know that this stands for all real numbers, right? This symbol right here stands for all real numbers. It can either be all real numbers, or it can be y is equal to a specific number. Okay, those are your only 2 options that you have for your range. Okay, now on the state test, okay, when you are going to be asked a question about domain and range, you are probably going to be asked a question about domain or range on either piecewise functions or absolute value functions, okay, which we have not covered yet. We'll do that tomorrow and Monday, okay? Those are usually the questions that you see your domain and range on, but it's good to know what it is for a linear as well. Okay, just the linear, it's a little bit easier to find out. They want to test you a little bit more than something pretty basic. Okay, we'll graph this here in a second. Okay, but because we've got this over here on that right side, we'll go ahead and fill that out for our quadratics. Okay, so thinking about a quadratic, what type of graph does a quadratic make? Does anybody remember the shape, what we called that? It had a weird name for a quadratic. Yeah, it's got the U. Do we remember what that's called? A parabola. Okay, so our shape here is a parabola. Parabola. That's how it's written. Parabola. Parabola. Okay. Now, we know that a parabola looks like a U or an upside down U. Okay. That's what it can look like for a quadratic. Now we're talking about quadratics. Okay? Does anybody remember the general formula or standard form of a quadratic equation? Does anybody remember that? Alright, so let's touch on it here. Our equation. Okay, y is equal to ax squared. Is this starting to ring a bell? What comes next? Plus bx plus c. Okay, y is equal to ax squared plus bx plus c. Okay, your rate of change. Okay, your rate of change is not constant. Look at our graph of what this graph could look like. It could be one thing up here, but then the rate of change is different right here because we're having to change, right? So that rate of change is going to be not constant. Not constant. Okay. Here, for our x-intercepts, I can either have 0 x-intercepts, I can have 1 x-intercept, or I can have 2 x-intercepts. Those are my only options. It's all you can have with quadratics. You can have 0, 1, or 2. Okay. All right. Your number of y-intercepts. Your number of y-intercepts is going to be 1. Okay. You're always going to have 1 y-intercept on your graphs. Okay, and you're always going to have 1 vertice. Okay, remind me again, I just talked about it here. What does vertice stand for? Minimum or maximum. You're always going to have 1 minimum or maximum. We sometimes see this called as our vertex. Vertex. I'm going to show you a way eventually to see how what our vertex is on the calculator. I don't think I covered that during the quadratic function. Okay, the domain for quadratic functions will always be all real numbers. Okay, and then for our range, it can either be y is greater than a number or y is less than a number, some constant number. Okay, and that number is always going to be the y value of your vertex. So the number being y value of vertex. Okay, any questions on those descriptions there? Everybody good? All right. This really should be a review sort of lesson. We've talked about all this so far, okay? But I do know some things get lost along the way, okay? Now let's look at what the graphs of these could be, okay? So my graphs of possible graphs that I could have, okay, for a linear function, okay? I can have something that looks like this. What type of slope does this linear function have? Positive. It has a positive slope. Okay, it is increasing from left to right. That means I have a positive slope. Okay, now I could also have a linear function that looks like this. Okay, what type of slope does that have? Negative. Now, at this point, these are two separate ones. I'm just giving examples. Okay, but what does this look like here? What did we talk about that this looks like? One of our bigger units.
Isn't it what there is the shaded part?
Okay, we did see it with inequalities as well. Okay, and you're on the right track. But can anybody come up with what this looks like when we have two equations on one graph? Anybody? No? Okay, this looks like a system of equations problem. Y'all remember that? Okay, and remember the solution for our system of equation is where you intersect. Okay, now it starts to make some sense. You remember that a little bit? Okay, this kind of looks right here like a system of equations. Okay, where my solution would be at this intersection. Okay, here's two possibilities of what a linear function could look like. Now, the third possibility that it could look like is this, a straight, and I didn't do a perfect job here, but a straight horizontal line is the only other one. Okay, why would this not be a function, a linear function? I can see the wheels turning in your head. Y'all know it. Okay, but why?
It doesn't have a value, so.
Okay, so imagine this was on a graph. Okay, I'm just putting it off the graph because this isn't a function. Why is this not a function? How can I tell if something is a function? Did we have a test that I could test it to see if something was a function or not? The pencil, what do we call that?
The vertical line.
Vertical line test. Would this pass the vertical line test? Does it touch my pencil in numerous spots? Yes, all throughout here would be touching my pencil in multiple spots. Okay, this only touches my pencil at one spot at a time, right? But this is infinite times that it's going to touch my pencil, so it would not be a function, right? Just like this would not be a function, right? Because it touches my pencil twice, right? Remember, your vertical line test is how you can tell if something is a function. And in this unit, we're talking about functions, okay? So that would not be a linear function. That's why you only have 3 possible ways you can see a linear function, okay? Any questions there? All right, for our quadratics, okay, going over to the quadratics, we said that I could either have 0 solutions. I could have 0 solutions. That would be like us seeing a parabola that looked like this. Why are there 0 solutions to that parabola, to that quadratic? It doesn't touch what? It doesn't touch our x-intercept at all. Okay, so that means there's 0 solutions, 0 x-intercepts. Remember, we talk about solutions, we say solutions, roots, zeros, or x-intercepts. Okay, those can be called 4 different things. Let's write that. Okay, zeros, solutions, roots, and then x-intercept. Okay, you can see those call any one of those 4 things interchangeably. And then over here we talked about the vertical line test. Remember that, vertical line test. Okay, the way you'll want to use a vertical line test on the state test is by looking at, it'll give you a problem and say which one of these function, or which one of these graphs is not a function. Okay, you'll be given probably 4 different graphs, and you'll have to use your vertical line test on 4 different graphs to tell which one's a function, which one's not. Okay. Now, we also said that we could see 1 solution, right? We said we could see 1 solution. So that would be like us seeing a parabola that comes down here and just touches 5 and then heads back up, right? It's just going to touch our x-intercept 1 time at that spot. Okay? That's an example of 1 solution, 1 root, 1 x-intercept. Okay? Then we saw where we could have 2 solutions. That would be like us seeing a parabola that goes above the x-intercepts and then back down, where it's going to cross our x-axis 2 times. Okay, these are your possible ways you can see a quadratic function. Those are the only 3 ways you can see a quadratic function. Okay, any questions there?
When you do vertical line test, if it's straight, like if you touch your point all the way through, what is it?
So it doesn't pass the vertical line test if it touches your pencil twice in 1 spot. So if I take this one, for instance, right, if I slide it from left to right, this 1 function right here is never going to touch my pencil 2 times, right, in the same spot. Okay, here, if I follow this one from left to right, it's never going to touch 2 times, right? Here, it's never going to touch 2 times. But if I had something like a graph that looked like a sideways parabola, right, that we saw here. Imagine this is my vertical line test, right? If I have a sideways parabola that looks like this, okay, it's touching my vertical line here once and twice, okay? And that makes it fail the vertical line test, okay, which means that that is not a function. Okay, same thing when we talked about this vertical, straight up vertical line. If this is my vertical line test here, and I'm using that, okay, well there's my vertical function. How many times does it touch it? 1, 2, 3, 4, 5, 6, 7, right? All those different spots, so therefore it's not passing my vertical line test. Everybody understand that there? Everybody good? Okay, remember you always have, Jalen pointed this out, you always have a vertical line with you, because you always will have a pencil for the state test. You can use your pencil on that screen to tell if it's a vertical line or not, okay? Alright, now let's go on and let's look at exponential functions. Okay, remember we had our exponential function unit where we had an equation that looked like y is equal to a times b raised to the x power. What makes this an exponential function? Okay, what makes it an exponential function is that x is in your, where is x? It's in your exponent. Think about exponential, exponent. X is in my exponent, right? That makes it an exponential function. Okay? Now, when we see our shape, okay, our shape would be called exponential. Exponential. Okay, but we know that that's going to be looking like a, kind of like an L almost. Okay, it kind of looks like an L or a backwards L. Okay, that could be what that could look like for your exponential function.
What is that above?
Above b, it's so it's just x in the exponent, but I circled it just to point out that it's in the exponent. Okay. Now, your rate of change. Notice here that this rate of change is moving much steeper than over here. So therefore my rate of change is not constant. So, which one was the only one that had a constant rate of change? Linear. All the exponential and the quadratic did not have a constant rate of change. The only one that has a constant rate of change is linear. Okay? Now, your number of x-intercepts, okay, you could have 0 or you could have 1. Which one is the only one that can have 2 x-intercepts? The quadratic, right? Here's exponential, we only got 0 or 1. Okay? Which one can have 2 x-intercepts? That's quadratic. Okay? Y-intercepts here, you can only have 1. Okay? There are no vertices because there's not a minimum or a maximum. Okay, so 0 there. Okay, and then your domain is going to be all real numbers every single time. So this is why, okay, they won't ask about domain really. I say they won't. Okay, they might. Okay, but generally they don't ask about domain for linear, quadratic, or exponential. Why? All 3 of them were what? All real numbers. So one thing that you might just put in your head and keep it in the back just in case is if it asks me about domain of linear, quadratic, or exponential, my domain's what? All real numbers every single time. Linear, quadratic, exponential, domain is all real numbers every single time. Everybody with me? Got me? Great. All right. Now range, okay, range is going to be y is greater than some number or y is less than some number. Okay, do you remember the word that we learned that started with an A when we talked about exponentials? It was when our graph approached a number. Does anybody remember that A word? Anybody? Nobody? Okay, that number here is going to be the value of your, anybody last chance? Nobody? Asymptote. Anybody remember that? I know you all remember it. Asymptote, right? Remember that's the x value that it gets closer and closer and closer to. Okay. Alright, so So possible graphs that you could see, okay, possible graphs that you could see. Remember, with exponentials, you are getting closer and closer to a number. Somebody pick a number for me on this graph. 5. Okay, so we're approaching 5. So I could have a function, an exponential function that looks like this, where I'm getting closer and closer and closer to that 5 value, but I'm never actually doing what? I'm never actually touching it. Remember, I gave the example of walking halfway to the wall each time? Y'all remember, if I walk halfway, I'm here. Okay, if I walk halfway, I'm here. If I walk halfway again, I'm here. Here, here. I'm getting closer and closer, but will I ever touch this wall? No. Right? If I'm actually walking halfway each time, I'm never going to touch the wall. Same thing here. That is your asymptote. What is that number I'm getting closer and closer to? My asymptote would be 5. Alright, now the other one that you could see something that looks like this. Say we're approaching, let's go the opposite direction and say it looks like this. Okay, that could be an option as well. That's what it is. So you can only see 2 different types of graphs for exponential functions. It's either going to look like one of these. Okay, everybody good? Alright, so let's try to think which one is a linear, which one is a quadratic. Okay, now, looking at my what values? Y. We know f of x is y. Okay, so looking at my y values, I'm wanting to notice my rate of change. Okay, which sometimes we call slope, my rate of change. How am I moving from one y value to the next? Okay, one y value to the next. How do I move from 5? How do I get from 5 to 7? I'm adding 2, plus 2. How do I get from 7 to 9? Plus 2. How do I get from 9 to 11? Plus 2. How do I get from 11 to 13? Plus 2. What do you notice? All of them are plus 2. So is this linear or is this quadratic? Linear, why? Linear because it has a constant rate of change. Linear because it has a constant, that's what's important, constant rate of change. Okay, now, what do you notice about 3 to 4? What do I do? Add 1. 4 to 7. Add 3. 7 to 12. Add 5, right? Add 5. Okay. From 12 to 9. I'm sorry, from 12 to 19. Plus what? Plus 7. Plus 7. Okay. Now the thing you want to pay attention to figure out, sorry. So you know it's not linear, right? Because it's not a constant rate of change. But you can find out that it's quadratic because these next values, if I take a look at these, what I just created right here, if I take a look at how do I get from 1 to 3, what is that? Plus 2. 3 to 5. Plus 2. 5 to 7. Plus 2. So if you go a second time and all of these are constant, that tells you you have a quadratic function. Okay, on that second time. Okay, now the rate of change here is different, right? We said plus 1, plus 3, plus 5, plus 7, right? That made it not constant. That made it a quadratic. Made it not linear right here. And then we knew for a fact that it was quadratic because these were constant. The second time we looked at it. Okay, because and I'll show you on the exponential is different. Okay, the way that they'll do this is they might give you this, and if these numbers might not add up, you would say neither. Say that, for example, forget these numbers over here, okay? But say that this was the second time we're looking at it, and it was plus 2, plus 2, plus 3. Do all those match on the second time we're looking at it? No, so you would say this is neither. This is not a quadratic or a linear. Okay, because this would have to be plus 2, plus 2, plus 2 for it to be a quadratic on that second time we're looking at that, right? Alright, so let's see what this looks like for our for our exponentials then. Okay, so with the exponential functions, how do I get from 1 to 3? Okay, I want you to think I can add 2, okay, but I want to see if there's a similarity. Is there something I can do to 1 to get to 3 that is the same thing I can do to 3 to get to 9? Multiply what? By 3. This is multiplied by 3. 1 times 3 is 3. 3 times 9 is, 3 times 3 gives you 9, so this is times 3. What is 9 times 3? 27, so that's what it did again. 27 times 3 is 81, times 3 again. 81 times 3 is 243. This is how you know it's an exponential function. Exponential functions multiply a constant value. So how can you determine if a function is exponential? By looking at the table. The y values are multiplied by a constant number. By a constant number. Any questions there? Alright, so let's take a look at this table over here. So I've got 3 different options. I've got linear, quadratic, exponential. So Jalen, are you even focusing, or what you got going on behind that computer that's so much more important? Huh? You sure? Because you seem interested in something back there. You good? You're not good. You are good. See, you're not even focused enough to answer questions. Shut your computer. Alright, we got 3 all the way. All the way down. There you go. See, now that phone's out of the way, you can focus. Alright. We got 3 different options. We got linear, quadratic, exponential. Okay, and we're trying to say which one of these match what's going on. Rate of change is constant. Is linear's rate of change constant?
Yes.
Yes. Is that the only one?
Yes.
Yes. Okay, linear is the only one that can have a constant rate of change. Okay. The second difference is, but not the first, because the first are constants. Okay, what do you think there? Okay, if my first numbers were not constant, but the second were, which, that was quadratic, right? If my first numbers weren't constant, but the second were, that means I have a quadratic function. Okay, which one of these linear, quadratic, exponential have a vertex? What's the only one that has a vertex? What do we think? Huh? Which one has a vertex? Y'all don't know? We talked about it. What type of function is this? Quadratic. What is this? Your vertex. Okay, it's also a maximum, right? That's quadratic is the only one that has a vertex. Okay, the only one that has a vertex. Okay. Which graph has no intercept? Are there any at all? Which graph can have no x-intercept? Can a linear not have an x-intercept? How many so let me ask it this way. Can a linear have 0 solutions?
Yes.
Yes. Can a quadratic have 0 solutions?
Yes.
Can a exponential have 0 solutions?
Yes.
Yes, so all 3 of them can have 0 solutions. So that means all three of them could have no x-intercept. They can have an x-intercept, okay, but they don't have to, right? That's what that's saying. Which ones can have 2 x-intercepts?
Quadratic.
Are there any more, or is it just quadratic? Just quadratic, right? Just quadratic. Quadratic's the only one that can have two x-intercepts. Okay, which graphs have at least one y, or which functions have one? I'll wait on you. No, it's alright. Alright, which graphs have one y-intercept? Which graphs have one y-intercept? Does a linear have one y-intercept? I say Jose, shake his head yes. Quadratic, does it have one y-intercept? Yes. What about exponential? Yes, right? So all three of them have one y-intercept. Okay, which ones have a domain of all real numbers? All of them, right? We talked about that pretty specifically, right? All of them have a domain of all real numbers. Okay, let's see. And then we'll spend some more time on range in a little bit. So the way that this works out, the one that is greater than would be exponential. The one that is greater than or less than or equal to would be quadratic. And then the range of all real numbers could be linear. All right, any questions there? All right, so determine which function is which, okay? What about what about this first one? How do I get from 1 to 2? Plus 1. How do I get from 2 to 5? Plus 3. 5 to 10.
Plus
5. 10 to 17.
Plus 8.
Plus 7. Which one is this? What about here? 1 to 3.
1 to 3. Plus 3.
2. Plus 2. 3 to 5. 5 to 7. So which one is this? Quadratic. Quadratic. Remember, exponential, we do what? Multiply. Did this multiply? Did this multiply? Yes or no? No. Was it a constant rate of change here? No, so that meant it wasn't linear. What's up?
So what is for linear?
Linear.
What you doing with that one?
All right, we'll see it here. Okay, so how do I get from 7 to 13? Plus what?
6.
6. Plus 6. 13 to 19.
6.
Plus 6. 19 to 25. Plus 6. 25 to 37.
6.
Plus 6. So which one is this? Linear, because it had a constant rate of change. Okay? Now, and then last, how do I get from 2 to 6, but also think about how do I get from 6 to 18? What would need to happen? Times 3. This is times 3. 6 to 18 is times 3. 18 to 54 is times 3. 54 to 162 times 3. Which would mean multiply, which is exponential. Exponential. Got too excited.
Alright, so you time. Can I get it out?
When you multiply those values, you're getting an exponential. Alright, so let's see what it looks like in the real world. Okay, now if you think about bacteria, okay, go into biology class. Okay, if you think about bacteria, you're saying I'm putting a little bit in there, and bacteria grows slowly or fastly. Anybody know? Pretty fast, right? And then it does what? It gets even faster, right? So think about what that graph would look like. It would be kind of something like this, right? Yeah? What does that look like? Exponential. All right, selling fruits and vegetables at the same price each day. That would be what? Linear, right? Because you're selling it at a constant price, constant rate of change. Okay, now what if I kick a ball in the air? what is that graph gonna look like?
It's gonna go up and
It's
down.
gonna-
Up and then down, which is a quadratic. Okay, and what I would do if I were y'all thinking about problems like this, I would think about it in my head. I would say, alright, if I have a soccer ball and I kick it up, right? So close your eyes, draw your graph. Okay, picture it in your head. Okay, that ball's going up, right? Then it's gonna hit a top point and then it's coming down. Okay, then open your eyes. What do I have? I've got a quadratic. Okay. Running a race at a constant speed. Okay, if I'm closing my eyes and I'm running a race and I'm running at a constant speed, it's not going up or it's not going down.
Linear.
Okay, well, actually mine went down because I had my eyes closed, right? But what is this? This is linear. Okay, a dead body decaying. That's gonna be exponential, right? Think about that. You're gonna start off here and it's gonna be good. Think about your funeral, right? Hey, I died right here. Okay, I'm dead. Okay, now y'all come see me. I'm still looking alright. Okay, then they put me in the ground. And then I look like a bunch of bugs and stuff, right? And that looks like what? Exponential. Okay, think about these things in your head. Come up with a scenario in your head. Make this make sense. Okay, appreciating value of a property. That's one that you got to think about. Okay, appreciating a value of a property. That's not me going up to Lacey and saying, "Hey, appreciate you for coming to school today." Right?
It's linear, cause it's.
That's what?
It's
It's going up. Okay. But it's gonna start going up fast. Remember, appreciating is almost like interest. Okay, what was the unit we talked about interest in?
I don't know.
We talked about it in exponential. Okay, you start thinking about appreciating. What is the opposite of appreciating? Depreciating. Okay, now think about depreciating. You bought the car, right? What do they say about a car? Right when you right when you drive it off the lot, depreciates like 10%. And it's dropping, and then over the years that car is losing value and value and value and value, right? So you started off, hey, here's when I bought it, okay, and now it's losing value. Okay, well, same about the house. Okay, what if I bought my house? Okay, I'll even use my example. I bought a house last year, or a year and a half ago. Okay, and I bought it for here. Okay, now it stayed about the same price, but they've started building houses in my neighborhood. Okay, and now my house is worth about $15,000 more because they're adding more houses in my neighborhood. Okay, so that's what an appreciating value of your house would look like. Okay, does that make sense? All right, so that's your exponential. Now, what if I jump from a high dive?
You're going down.
That would be like this, right? I'm at the diving board, right? And then I'm getting down. Now, think about it, right? When I hit the ground, do I shoot back up?
No.
No. Okay, so that's gonna leave you with an exponential.
I thought it was linear.
I thought it was concrete. Cause you said if it's going down. Man, I don't know.
Okay, I can see how you could do it either way. Okay, we can make an argument either way. That's probably not the best one. Okay, I can see jumping from a high dive looking like this, right? I can see it. Okay, let's give an example of a linear one. Okay, let's say that your graph starts here, right? And you dive, you might look like that, right? And that would be kind of what it would look like linear. Okay, but I can also see it as quadratic. Well, what if I am including my climb up the ladder? Well, I'm getting up and then I'm jumping down, right? I can see the argument for that. Okay, and then I can also see the argument of maybe flatten out and then I jump. I can see that direction. Okay, so that's probably not the best question. Let's not get stuck on this one. Probably not the best question there. Okay. The state test is not going to give a question as unclear as that. Okay. All these other ones I think were good ones, except for this one's probably not the best example. Okay. Let's see. I think we want to call it there for today. So we'll end it there. Okay. You've got 3 assignments on Khan Academy for today. Okay. One of them is going to be on on solving equations. I would try to do that one first, because you have your calculator and you can use that solve method that I just